Okay, we good? So I took some examples from the slideshow yesterday to make our lives a little bit easier. So it's going to seem a little repetitive, but it'll be good for you. It'll allow us to get into all the fun stuff. All right, so we're going to talk about properties and limits. They're pretty easy. We'll get to them in a second. We'll talk about some strategies, because when the functions get weird or the picture looks weird, you're going to need to have some different ideas on how to find the limit. We're going to divide out and rationalize. We've done the divide out already. That's the whole canceling that we did yesterday, but we are going to have to talk about rationalizing, which will involve things like, well, we'll just wait till we get there. That'll be fun. Talk about the squeeze theorem, also known as the pinch theorem, also known as the sandwich theorem, depending on who you talk to. And then your challenge for today, fit 20 grapes in your mouth without joking.
I might have grapes for lunch.
You got 20 of them?
Probably.
Beautiful. Are you accepting the challenge?
Yeah.
Awesome.
If I've got grapes, I normally
What's that?
I feel like that's an easy way to show.
Well, I was very specific. This way I'm covered in a court of law.
Yeah, you're
Right? I mean, when you get called to the stand, they'll ask you a simple question. Did you see the slideshow that says without choking? And you would say, yes. And then you would say, but Cam died. And they would say, yes. But did you see
I
this?
definitely have 20.
Awesome. Remember, without choking.
Without choking.
Okay, let's talk about these three first. A lot of what's going to happen is I'm going to give you information and then ask you to discuss it, or we're going to discuss it. I'm not a fan of memorizing. The exception is there's two theorems today that I'm just going to have you memorize. These, however, I want to talk a little bit about why they're true, because I think if you have an appreciation for why they're true, you won't get bogged down in trying to memorize stuff. You'll understand why it works. So, for instance, we'll take the limit of b. b is some number, it doesn't matter. As x approaches c, that's going to give us b. Why does that work? What's the graph of b look like? Let's say the limit of 7 as x approaches 2. John?
Because it's a flat line.
20. 20, right?
Hold on. You got 20? Good. Don't chew them. Just spit them into Kevin's hands. He's gonna start.
He's got
He's gonna
22.
be looking. 14?
20.
20? More. I understood perfectly. Good. Nicely done. Yeah, you get to a point where you're like, okay, I'm safe now. I'm not gonna choke it. When that first bite, when you start, you're like, wow, that's a lot of grape juice.
It's a lot of juice.
Right, you don't want it to run out of your mouth and everybody's staring at you. You don't want to be that guy who's got the grape juice. You okay?
Yeah, that was.
Brandon, you all right? Are you past the point of no return?
No,
You haven't died,
two
so
more
you're okay.
seconds. 2 more seconds. That was exhilarating.
And you went back for more.
Gotta
Feel
finish
bad
it.
you're
Now you got
deprived.
no, yeah, now you got
I should have gotten 23.
What are you gonna do for lunch?
I still have a ton of food.
Awesome. All right, John, back to you. Sorry for the interruption. Why is the limit as x approaches 2 of the graph of 7 equal to 7?
It's a horizontal line, so no matter where on the graph, it's going to equal that constant b.
Perfect. Everybody good? Beautiful. Part 2. What's the limit of x as x approaches c? Why will it always be c? What's the graph of x look like? What kind of line? Okay, could you be more specific than this? What does that mean?
Like a 1-to-1 slope ratio going through the origin line.
Does that work for everybody?
Yeah.
Beautiful. 45-degree angle.
Okay, that's what I was looking for.
Where all the x and y points on that graph have the same coordinates, so therefore no matter how far you move up, you'll also move over the same amount.
That's nice.
All right, what about c? No, that's a 3. What about 3? Can you believe we're in the 3rd week of school and it's still August?
Yeah, we're almost at final started if you think of it that way.
Yeah, that's so true.
If you're taking that at first grade, you would
His
Wait,
estimation
question.
skills are a little. don't even have a comment. I don't know what I'm doing anymore. My pen's not working. There we go. Okay, so hi, how you doing? Good, go away. Thank you. Why does that keep showing up? Stop. All right, I'm doing this. There you go.
So what was the third one?
2. Maybe see that condor that just flew by? Oh my God, it was the size of a small child. I think it,
I
tough
don't
to
think we
call.
had condors.
Mine's in Phoenix.
Bill Rising.
I don't think you need to write all this down because it's pretty straightforward. You've done this before. They're the same properties that you use like when you did logs. So the limit of a function times a number, also called a scalar, is just going to be the limit times that number. In other words, just bring the number out in front, find the limit, multiply your answer by that number. The limit of a sum is the sum of the limit. The difference of a limit is the limit of the difference. Product is product. Division is division. Power is power. Okay?
I like it a lot.
I'm glad. So forget about the work that I'm about to show you. What's the limit of that function as x approaches 2? Hi. Yeah, that'd be great, thanks.
17, 19.
Getting different answers.
19.
19? 19. Why?
16 plus 3. 19.
There you go. First thing you should always do in a limit problem is plug and chug. This, however, and the properties on the previous slide are an explanation as to why you can plug and chug. Old school method would be to say, okay, well that's a limit of a sum, therefore I can do the sum of the limits, and then apply all these other techniques to get down to the answer of 19. But like it says, we would just plug and chug. But that's what allows us to plug and chug, using those properties. Limit of a sum is the sum of the limits. Scalar times a limit is the scalar times the limit. And then we talked about that property already. Taking the limit of a constant will just give you that constant. Okay. So we talked about this yesterday. Can't plug and chug. Right? Get 0 over 0, which is bad. So then you need to figure out something else. And in that case, we factored the top and bottom, canceled, and then plugged and chugged again, and we get 3, which is what we got yesterday, correct? Good. All right, so no big deal. That's the first algebraic strategy. The second one is a little nasty. That's similar to the example I had yesterday where I think it was Kevin who gave us an idea of what that graph looked like. I just took the function, I flipped it over. No particular reason except it's a little bit easier to see. We're going to use a conjugate. Do you remember what a conjugate is?
No.
Yeah.
Conjugated verb. It's different.
No.
Isn't it like,
Silly.
wouldn't it be like, if you've got like x plus 7, then the conjugate would be x minus 7. So you're gonna wanna cancel out.
So if I have, let's use Cam's example. If I have, do you start with x plus 7?
Yeah,
So he started with x plus 7.
in the denominator.
Its conjugate is x minus 7. Why do I care about the conjugate? What happens when I multiply those two things together?
Cancels the middle term.
Middle term disappears, so we get x squared minus 49. Same is going to happen up here when we use the conjugate of that numerator. So what's the conjugate of the square root of x plus 1 minus 1?
X plus 1 plus 1.
Perfect. Okay, good. So like I said, can't plug and chug. We did that yesterday. So here's the conjugate. And I have to multiply by the conjugate over the conjugate. Why? What is this equal to?
1.
1 doesn't change the value of the function, which is good. If you change the value of the function, you've done something wrong. When I multiply out that numerator, what will I get?
X plus 1 minus 1. So x.
Everybody follow that?
No.
All right.
X.
Here are our first two terms. Here are our last two terms. So the first two terms multiplied together gives me x plus 1. Because the square root of something squared is it something. The middle term's going to drop out because that's going to give me a negative square root of x plus 1, a positive square root of x plus 1. That goes away. Negative 1 times negative 1 is negative 1. And negative 1 minus, or 1 minus negative 1 is just plain old x. Okay. Which works out perfectly because there's an x in the denominator. Which we can cancel. Then what?
Then you plug and chug.
Plug and chug. Bring that limit back in there. Plug and chug.
Can you go back to one so
Yeah,
I could?
Sure.
Mr. Reedy, how do you end up with, on this third one, how do you end up with just an X on top?
Because this mess up on top, when you multiply it out, all equals x.
Oh, okay.
Get that nice pretty answer of 1/2. Are there other ways to find that? Yeah, if you had a calculator, you could graph the function, see what it gets very close to as you approach 1/2. But that would be the algebraic manipulation of that function that I talked about yesterday. Question in the back.
For the AP test, will you have a calculator for the whole thing?
Nope. 4 parts of the AP test.
So 2
Four.
calculator, 2 non-calculator?
Show your work, multiple choice, show your work, multiple choice. It'll be fun. 4 hours of bliss. Depending on what crew you're hanging around with, they may refer to this theorem by different things. The squeeze theorem, the sandwich theorem, or the pinching theorem. And since I want you to be globally knowledgeable, I introduced you to all 3 terms. I usually call it the squeeze theorem, but again, you're more than welcome to call it either the sandwich theorem or the pinching theorem. Squeeze theorem because the 2 functions squeeze together. The sandwich theorem because you think of the 2 functions as bread and then the other function as your slice of luncheon meat. And then the pinching theorem is the same thing as the squeeze theorem, just another word for squeezing. So here's the idea. We've got 2 functions. In this case, I have them illustrated as purple or pink, whatever you want, and blue. Top one is g, the bottom one is h. And those 2 functions are getting closer and closer to some value. In other words, the limit of g as you approach c is going to that value, and the limit of h as you approach c is going to the same value. Okay, so you can see now why it's called the squeeze theorem. It's squeezing down to a point. It's pinching down to a point. Or it's a lunch meat sandwich because you got 2 pieces of bread and a piece of bologna. That's the setup. And I'll give you the details in a second. If f has to always be between g and h, what can you then tell me?
G is greater than F.
Good job, Sam. Let's just move on.
Wait, will the limit always, will like, that g and h meet, will the limit always be on f?
Well, that's what the theorem is saying.
Okay.
Okay. So if the limit of h as you approach that value is equal to this value of the limit, and the limit of g as x approaches c is that same value, and there's the beginning restriction that f has to always be between g and h, then f has to approach that same value. Okay? You think about having a sandwich here. You got 2 pieces of bread and a piece of bologna. You smash down the sandwich, the bologna's not going to just fly out of the sandwich and end up on the other side of the bread. It's going to stay between the 2 pieces of bread. The same is true here. As you start to pinch those functions, and they get closer to that point f has to get closer to the same point too. It can't all of a sudden magically fly out and be on top or below the other 2 functions. Okay? Does that make sense? Yes or no?
Yes.
Okay, good. it's not the most practical theorem, and I have an example which will scramble your noodle a little bit, but you'll see why it does exist. These are the two theorems I talked about. We could go into the derivation of those theorems, but it wouldn't be worth our time, and you wouldn't enjoy it. So I'm contradicting myself today and saying here are two theorems that I just want you to memorize. And we need those theorems to do the next example. Pregunta?
Well, I mean, it would just be a derivation question, so no.
So the next example I have is an application of the Squeeze Theorem, so you can see how it works. Okay, we good?
It's been a pretty slow treat Tuesday, if I do say so.
I'm a little hungry actually.
You're hungry, you just ate 20 grapes.
23.
23, sorry, 23 grapes. But you're still hungry.
Yeah.
Brendan, are you hungry too?
Not really.
Because you had 20 grapes.
Yeah.
Yeah.
Got a fast metabolism.
It's been like 7 minutes.
It's probably
Wow,
almost out.
Brendan's like
Oh boy, okay.
tangents.
So change the rules a little bit and change the theorem. So tangent of x over x. Pull out your calculators. Graph that bad boy. Make sure you're in radians. See if you can use your calculator to find the value of that limit.
Yeah. Wasn't that a work problem?
Hold on. What's the first thing you should do before you even start working with the calculators? In any limit problem,
Plug and chug.
plug and chug.
Over 0.
Wouldn't that be fun if it just had an answer there? Yeah, it doesn't. What's the tangent of 0? Oh, it got quiet in here. What's the tangent of 0? What's the tangent of 0?
0 over 1.
No, isn't it?
0. Yeah, so we have 0 over 0, which doesn't work. Question or answer?
No, like, I don't like the way that works.
Calculator's all wonky?
Yeah.
Are you in parametric mode?
Do I do?
Are you sure you're not in parametric mode?
Maybe your x.
Are you, holy smokes. Invalid ID dimension. Well, let's quit it.
Sweet deal.
I did that yesterday too.
I fixed this. I just hit the button and quit it.
I don't like the way this looks.
Should be able to. Whoa, what the heck? You didn't say you correct.
Oh, okay.
Oh, that's
Super
the way.
big balls
I
going all
fixed
over
it.
the place.
I turned off the,
And then it looked like a
snap line.
microchip.
Okay, so 0 over 0 doesn't work. We'll come back to the algebraic manipulation in a second. However, let's see what the calculator tells us. Does the calculator give you an indication of what that limit might be? What would you like to set your window at? Because if you just graph it, you're going to get a whole bunch of swirlies and loopy things and parabola-looking things. What would you set your x values at? Say it loud, say it proud, John.
-1 to 1.
Good call. What'd you set your y values to? I don't know. Does it have a parabola around the,
Yeah.
up there? So you'd have to get down to like that parabola in there. And where's the, where does it cross the y-axis then? So we're guessing the answer might be 1?
Sure.
Alright, so we'll see. Hit the table and see what it says for 0. It should say error, but maybe we can change that.
Hit the what?
Second graph. It's a table.
Table, correct. So it says error at 0, but we knew already that it would say that because we did the plug and chug and 0 over 0 doesn't work. You could look at values above and below on the table and see if it's approaching a number. Does that give you any indication? Or is it too big of a jump? Too big of a jump. Then change the jump. Go to table set and change the delta t or delta x to like 0.1 or 0.001.
You can just do second calc and 0.00000001.
You could do that also. And what is the answer it's giving you? What did we think it is? 1? All right, let's look at the algebra now. I had 2 theorems that might come into play. If I'm not sure what to do, I don't know how to work with tangent, the first thing I would do is rewrite tangent as sine over cosine. What's this equal to? 1. What's this equal to?
Let's just say 1.
1. It is 1.
Why is it 1?
Because 1 over, or the cosine of 0 is 1, so 1 over 1 is 1.
Rewrote this algebraically to be sine over cosine. Paired up the sine of x with x because I have a theorem to deal with that. That was in a couple slides ago. This I can just plug and chug. Cosine of 0 is 1, 1 over 1 is 1. So we end up with the limit of a product being the product of the limits. That's 1 times 1, which gives us that answer of 1, which we got from the calculators. Pregunta?
Yeah, what could be messed up with my calculator that it gave me a 0 value? And it's in like gradients too.
No
so-
sick.
Cause maybe my calculator's just messed up.
You should go get a new one.
10, 9, 10. This is my graph.
Okay, so we did that already, and we're good to go there.
Did you try turning it
Okay.
on?
Look on.
Okay,
Yeah. I got it.
now let's talk about this guy. Squeeze theorem, sandwich theorem, pinching theorem. Remember yesterday or the day before I talked about a dampening function? That's what we got going on here. So I can't take the limit because this function oscillates back and forth. Okay, by the way, that function is that mess. I plug and chug, it doesn't work. Okay, I get 1 over 0 times a sine, it's a train wreck. So here's the process I'm going to use. I'm going to start, let me explain what's going on here. I started with the sine of some value t. And I know from my vast stores of trigonometric knowledge that sine is always between 1 and negative 1. You with me? Good. Then I said, well, instead of t, I'm going to put in 1 over x squared. Why 1 over x squared? Because I got a 1 over x squared right there. It doesn't matter what you put in for sine. The sine of anything will always be between 1 and negative 1. So this almost matches the function I'm looking for, except I need an x squared to multiply it by. So I multiplied the middle by x squared. If I multiply the middle by x squared, then I get the outsides being multiplied by x squared also. Now, why do I care about that? Well, what I've done is I've set up the hypothesis of the squeeze theorem. I've taken a function and I've sandwiched it between 2 other functions, which is shown in the picture here. There's the top piece of bread, which is x squared. There's the bottom piece of bread, which is negative x squared. And I've guaranteed that that function is always going to be between the 2. Okay, so yeah.
So like this, when like you have to like multiply each side by x squared, is that similar to when we have to do like when you have to find like the period in the sine and cosine graphs?
Yeah, where you set the function equal, you put it between 0 and 2
Yeah.
pi. Yeah,
Okay.
I wouldn't say identical, but it's a similar thing. Okay.
Didn't you say there's like no period if it, or no limit if it oscillates?
We can't find the limit if it oscillates, so what we're going to do is cheat and use the sandwich theorem and say, well, I can't find the limit of that function, but I can use the squeeze theorem to get that limit based on other functions.
Okay.
That make sense?
Yeah.
Okay. Yeah, normally you wouldn't be able to just take the limit of that inside thing because it just keeps bouncing up and down. Are we okay with the setup here? The rest is easy. Once I establish what this is between, then I just take the limit of these 2 guys. What's the limit of this as x approaches 0? What's the limit of x squared as x approaches 0? 0, good. What's the limit of negative x squared as x approaches 0? 0. This is always stuck between these two, so therefore what's that have to approach?
0.
Nice. So when you want to use the sandwich theorem and or apply the sandwich theorem, you have to build your function from something very basic. So I started with a basic sine function and got to the function that I'm looking for by adding on to it. So I changed t to 1 over x squared, then I multiplied everything by x squared. And I end up with the center part being this weird function that I don't know how to find the limit of. But I also ended up establishing that the two pieces of bread were x squared and negative x squared. And I can find the limit of each of those as they get closer. Now, if that limit's not 0, we have a problem. Let's suppose I say, well, what's the limit when x approaches 2? That's a different animal because it's not being pinched down at 2, it's being pinched at 0. Okay, you can only talk about the sandwich theorem, squeeze theorem, pinch theorem when you're getting close to a value, when both the top and the bottom limits approach the same value. Okay? How we doing? Doesn't come up very often, but you should know how to apply it when need arises. Little help for you on